Have you ever really stopped to think about what's happening when an egg fries or a nail rusts? It's not magic, it's chemistry. And today we're going to crack the chemical code. This is the hidden language that describes all the amazing, invisible changes happening around us all the time.
So let's start with a few things you've definitely seen before. A couple of, well, let's call them everyday chemical mysteries.
You know what happens when you leave milk out for too long, right? The smell, the taste, everything about it changes. It becomes something completely new. Or how about a cast iron skillet or some tools left out in the damp air? Before you know it, you've got that flaky, reddish-brown stuff we all know as rust. And maybe the simplest one of all, cooking. Think about it. You take a bunch of raw ingredients and you turn them into a totally different meal. So what's the big idea here? In every single one of these examples, the stuff we started with has fundamentally changed its identity. This isn't just like ice melting into water, which is still H2O. No, this is a full-blown chemical reaction. Okay, so how can you tell if a chemical reaction has actually happened? Well, you can be a detective and look for some classic signs. Did the color change? Are bubbles of gas suddenly appearing? Did it get hot or cold all of a sudden? If you see any of these clues, you are literally watching chemistry happen right in front of you. So, how do we actually describe these amazing transformations? Scientists, of course, needed a really clear and universal way to write down the story of a reaction. The most basic way to do this is with a word equation. It's super straightforward. On the left, you've got your starting ingredients, magnesium and oxygen. We call those the reactants. And that arrow, that points to what you end up with, magnesium oxide, which we call the product. Simple, right? But, writing out all those words is a bit of a drag. So to make things way more concise, we use chemical symbols instead. That long word equation just becomes Mg plus O2 equals MgO. Now that's a proper chemical equation. But wait a minute, take a closer look at that equation. Does it seem totally right to you? This is what we call a skeletal equation, and it's kind of telling a little white lie. It's breaking one of the biggest rules in all of chemistry.
To tell the whole truth, we have to become, well, atomic accountants. We have to balance the books and make sure every single atom is accounted for.
And here is that number one rule, the law of conservation of mass. This is a big one. It basically says you can't just create matter out of thin air, and you can't make it disappear into nothing. The atoms can rearrange themselves, sure, but the pieces you start with have to be the same pieces you end with. And that is exactly why we have to balance equations. It's our way of proving we've followed the law. We need to make sure that the number of atoms for, say, iron on the left side is the exact same as the number of iron atoms on the right side. All right, let's walk through one. Think of it like a puzzle. First, we do a quick count. And yep, the numbers are all over the place. So let's start with the most complicated part, the Fe3O4. See those 4 oxygens? We need 4 on the left. So we pock a big 4 in front of the H2O. But oops, that messes up our hydrogens. Now we have 8 on the left. No problem, we just put a 4 in front of the H2O on the right. Almost there. We have 3 irons on the right, so we just need a 3 on the left. And voila, everything matches. The equation is balanced.
Okay, so once you get the hang of balancing equations, you start to see patterns. You start to recognize different types of stories or genres that pop up all the time in chemistry.
Let's start with 2 that are basically polar opposites. In a combination reaction, simple things come together to make something more complex. Then you have decomposition, which is the exact reverse. One big thing breaks down into simpler parts. 2 sides of the same coin, really.
Reactions also tell us a story about energy. An exothermic reaction is one that gives off heat. Think of a campfire, or those little hand warmers you shake to activate. Heck, even the reactions in your body keeping you warm right now are exothermic.
And on the flip side, you have endothermic reactions. These actually have to suck in energy from their surroundings to happen. The perfect example is one of those instant cold packs. You crack it and it gets icy cold because the reaction inside is pulling heat from everything around it. Then you've got reactions that are all about swapping places. In a single displacement, one element basically cuts in and boots another one out of a compound. But in a double displacement, it's more like a dance, where 2 compounds swap partners and form 2 completely new couples. Okay, let's bring all this theory back home and talk about one of the most important types of reactions you will ever see, oxidation.
So, what is oxidation? Well, at its heart, it's really simple. It's just what happens when a substance gains oxygen. That's it. But that simple process shapes so much of our world. And believe me, you see the results of oxidation everywhere. That rust on iron, that's just slow oxidation. The tarnish on silver, oxidation. And that not so great smell when food goes bad, that's rancidity, which is what happens when the fats and oils in the food oxidize. And here's a fantastic little piece of everyday chemistry. You ever wonder why a bag of chips feels like it's half full of air? Well, it's not air, it's nitrogen gas. They flush out all the oxygen to stop the oils in the chips from oxidizing, which is what keeps them so crispy and fresh. Pretty smart, huh? So you see, chemical equations aren't just some boring thing from a textbook. They are the written language for all the invisible, amazing changes happening constantly. They tell the stories of our world. So now that you know how to read the code a little, what chemical stories are you going to notice happening all around you?